Hello and welcome. I'm Shadow of Shadow Gaming, bringing you Programming with Shadow, episode number 60. In today's lesson, we are going to be doing another sorting algorithm. This one's called Heap Sort. So in doing this, in preparing for this one, I had the thought that maybe this is the wrong order and we should look at a heap first. I probably should, but I'm not going to do that since we're already on sorting. We're going to look at a heap in very basic terms and then go ahead and implement it. And we'll come back later and actually look at the algorithm or at the data structure more in depth. So let's begin by creating some files here. We'll create a new class Heap Sort. And we'll create a new text file. New item text. Also calling it Heap Sort. And we'll copy our array here. So this is actually an interesting array to demonstrate a heap sort with, because what we'll find out is that it's already in the correct order. So what's a heap? So in computer science, there's a concept of a tree. And here I'm going to use different values just for the sake of different values. So we'll have 10. Let's see if I can do this. Let's do 5, 3, needed over one more space. Almost had it. 3, 2, let's do this. I'm trying to make sure I have enough space here. I think I want that. Yeah. Okay. So let's say that this is a tree. So in C# or in programming or in computer science and programming, you'll see a tree like this. It starts at a root and goes down, which is sort of the opposite way of a tree, and you'll occasionally see memes related to that. But this is how you would do a tree, and there's usually a good reason to, because, for example, if there was some way you could navigate this tree, like say you wanted to find, get down to this node, notice there's only 1, 2, 3 steps you need to do it, and you're there, rather than if you had an array and it was all listed out and 2 is the last element, you'd have to go through every one if you didn't know exactly where it was or something like that. And those are nice because they give you logarithmic, or big O of log n. And we're going to see that heap sort takes advantage of that. So a tree, you could have any number, like this is a tree. You could do it like this as well. Five, 3, 2, 7, and then delete all these other ones. Oops. That's a tree too, it's just a bad tree. So that with a tree, there's the idea of it being balanced or not. This one is unbalanced and the linked list. So it ends up being a linked list instead of a tree. But it is a tree. It's just an unbalanced tree. So when you do the trees, though, you a lot of times want to keep it a little more balanced, and a heap's a very balanced tree. For a heap, you follow this order. You always start here, and you fill out these spaces, and then these spaces. And then next one you would add a new layer and fill them out left to right as well. Notice I left a blank one here. We're saying we don't have enough values here. And we're going to see that here for 5 values, we're going to have 1, 2, 3, 4, 5. And we won't even have anything here. So that's very, very basic of what a tree is. So one property here we can mention, height is log n. So 1, 2, 3, 4, 6. So there's 6 elements. Log of 6 is, I have to pull out a calculator for something like that, actually. I should know it, but I did not. The log of 6 is 7. All right. I think that's right, yeah. Yeah, so we're saying it's 1, 2, 3. Should be 3 layers. Maybe it's ln. Maybe I'm wrong on that. I would have thought that would have rounded up to 3. Maybe it's 2. Maybe I'm thinking of it wrong. Maybe it's let me pull calculator back out. So 1, 2. How many did we say this is? 6 elements? 6, 7, 8. Let's add 9. So 9 ln 2 and round up to 3. Okay, so believe that's what's happening. So this is layer 1, this is layer 2, layer 0, I guess, and then layer 3. That may be what I'm trying to remember. And that makes sense. So the reason to use ln instead of log n, ln is the natural log, and they're a lot closer to the log of base 2. So with the reason it's base 2 is there's 2 paths here. If you had a different tree with more branches, then you would use a different log, but for binary, log 2 actually makes sense. So the heaps we're going to deal with today are called max heaps. You can also have min heaps. You basically just flip the order of the signs and the operations and get a minimum heap. So the thing a max heap guarantees is that parent is larger than either one of the children. So this one is not a max heap, so this one's invalid. To make this one valid, this would actually need to swap places. So you'd have something like this instead. However, now it matches, even though 7's bigger than anything here, there's a duplicate 3. It guarantees that it's larger though, so 5 and 7 are both smaller than 10, 3 and 5 smaller than 5, 3 and 7 smaller than 7. So it does not make any guarantee here, like these could be any value as long as they're smaller than this one. The other nice thing with a heap versus some other structures is because everything's complete, we always know the size, it's 1, each layer is complete, we can store it as an array. So let's look at an array here. Like I said, I actually got lucky with my pick here. Back whenever I picked these numbers, they already work as a heap. So if we build the heap, so we'll take the first value and we'll make it the root here. All this. So let's build our heap. Let me leave that in. So 5, and then we'll make these underscores. Underscore. All right, 5. And now there's no other value, so we go to the next index. Now we get a 3. We fill left or right, so we go here. But that's not how it inserts. So the correct way to insert into a heap, I can think, let me think just a second. I guess, yeah, this works. So, yeah, I think I would insert it here, and then we would compare and see if it matches. We're using a max heap, so we say, is it less than? And if it is, we are good. If it isn't, then we have to do a little more work. Like I said, in this case, the heap just so happens to work out perfectly. So I guess we don't actually need to see that for our example. The next index would be here. Then we would plug in a 1 here, and a 2 here. So yeah, that one's actually not interesting, but let's copy this. Let's do one more example, and let's try to make it a little more interesting. So let's make the 5 a 3, and let's make the 4 5 and 4. Not going to be a ton more interesting, but a little more interesting. We take the first value in 3, then we take the second value in 5. And now we have to do something called heapify, so the values don't match here. So what we would have to do now is actually work our way back up through and see what the correct order is. In this case, it happens to be this and this. Although that should be a 4 instead of a 5. I can't even read my own example after I wrote it. Then we do a 5 here. Now we run into a problem. Now 5's bigger than 4. Now we have multiple values, so now we'd have to compare, this one bigger or is this one bigger? Because this one's bigger, it goes on top, and we swap their places. And then we would keep going, and the rest of the heap works out. That's a very rough, very, very quick introduction to a heap. Like I said, we'll look at this when we actually look in the data structures a little more, but from here it becomes really easy. So once we've got the heap laid out, all we got to do then is extract the values. So if we take this, oops. So here's our final array. All right, so we take the first value, which is 5. Then we recorrect the heap. We take the value and we move it to the end, I think. So it goes here. And then we have to do that heapify thing. So we compare both children, 3 and 4. 4 is bigger, so we make that swap. Now we check 2's new children. There's no children, so we're good. And then we can just remove 5. It becomes an underscore. Then we do it again. So now we do 4. We move it to the place of the last item, which is there. Then we put a 1 there, and then we perform heapify. Is 3 bigger than 1? It is, and 2 is bigger than 1. Yes. So now of these two, 3 is bigger. Move it there, and then 1 goes here. We do not count the 4 here because as we mark through the array, we mark off that last position because the last position gets extracted. And because we're doing max heap, we actually need to do it the other way. It should be going into the array like this. That way we don't have to reverse it at the end or anything. So something like that. Now we extract a 3, and then, again, these take place of the lowest position. And we're going to extract a 3 because there's no need to heapify at this point. And we do it with 2. It is now sorted because there's only one value. It makes it really easy to sort. Oops. And now there's just one value, so we just take it and we are done. That's roughly a heap sort. Like I said, this was very quick, very rundown. So we'll implement it today, and like I said, we'll plan to, in the future, we'll move back to data structures probably very soon, and we'll get into trees, and heaps will be as part of a tree. Let's do this. So we'll copy our method here. You may want something like that, but we're not going to do that exactly. So here we go. Here's our sort. So these are all correct. Space complexity. So space complexity, it looks like we were doing more work than we would need. just looking at this, it looks like I was creating new arrays and everything. In reality, we're just using the original array. We're just adjusting how things are stored in it. So this one has a space complexity of 1. So it uses the exact same array you give it, so no new change to the array. So merge sort was in, it uses, or it grows linearly. Quick sort was average is log n, so a little worse than heap, but worst case was n. So heap sort's the best we've actually seen of the n log n algorithms, and that's why if you look in the standard library, for large values of n, heap sort's what's actually being used, and that's because of this. It has better space complexity and doesn't run into worst case problems here. So stability, it is not stable. So if we have multiple values, like if we had their original heap up here where it has 2 3s, you have no guarantee whatsoever that you're going to get the 2 3s. So it could be either one of the 3s. You have no guarantee there. It is in place, so that's why the space complexity is so good. Is it's an in-place algorithm. All right, so let's begin. So the first thing we want to do is we want to build the max heap. Then we want to sort the array. So those are the 2 steps. The very first thing we're going to do is we're going to say for int I equals array.length. So here's the fun part. Divided by 2 and then minus 1. I greater than equal to beginning of the array, so 0, and then I minus minus. That was completely wrong keys. Here, we'll do something here. So what's happening with that? That looks confusing. So what's happening there is we're getting half the length and we're subtracting 1. So that gives us something like, for our example here, we get the length, which is 5 divided by 2. So 2.5. So we don't do halves, so 2 minus 1 gets us 1. So that gets us our I here. What we're going to use I for is where we're going to be swapping around. So whatever's in position 0 is going to stay the same. So we get a 1. However, we're going to be decrementing. So we're going to swap the position at the end with I. And we just go to 0 and we do that swap again. So that seems very questionable. What's that actually doing? So on the first one, let's use our example here. Like I said, this isn't a good example because it's already sorted. I might want to use the other one, but we'll use this one. So the first pass, we get no, well, like I said, we end up with no change. So we start here with I and this one, and we compare the 2 end positions. So if we look in the array, 5, 3, 4, 1, 2. So we're comparing these two, 3, 1, and 2, and we're seeing if they need to swap places is what we're doing. I'm actually having trouble saying that out directly with that algorithm. So what we're trying to do is we're trying to make sure this subtree here is in the heap order, so this one's greater than both children. And then we'll say this one side that is, and then we'll say the entire thing is. And that's what we're trying to do. We're trying to build up recursively, I guess. So we're trying to build up and say this subtree's good, this subtree's good, this subtree's good, therefore the tree's good. That's what we're doing with this. That's what's happening here. And for that, we'll call a method called heapify. We'll pass it in our array.length. And I think. So let's implement that. Private static void heapify int array int heap size int root. Okay, so we're using I to say where we're rooted at. So as we do the individual subtrees, I will change. So that tells us what we need to worry about. I'm going to collect some variables first. So let's say int largest equals root, int left equals 2 times root plus 1. So int right equals 2 times root plus 2. So why does this work? If we get our array back here, and this is the correctly sorted one. So what's happening here is this. So let's say the root is 3. So it just so happens to work out with the heap array that 2 times this index, so 2 times 1 is 2, plus 1 is here, plus 2 is here. And that gets you the, or if it's a binary tree, which is heap is, it gets you the 2 indexes that are the children of this position. And that works for bigger arrays as well. Like if we have more values in the heap, that ends up working out for you. So you get the left and right child of your current root. In doing that, you're able to do the comparisons. So now we'll say if left is greater than heap size and array at left is greater than array at largest. Then we'll say largest equals left. So right now we're saying is the largest bigger, is the left side bigger than the root? We'll need to do it with the right side as well. If right of heap size and array at left greater than array at largest. So important that we keep track of the largest there. Largest equals right. So now we're saying, okay, is left bigger? If it is, we make left bigger. Then we say, is right bigger, still in the heap? And if so, is it bigger than the largest? And if so, right's the bigger. And then at that point, we just have to swap them. If largest does not equal root, awful time typing. Utilities.swap array root largest. And we are almost done. However, it's a tree, so right or whichever one was the largest can also be a subtree of themselves. So then you need to heapify array heap size and largest. And there we go. So that should get us our heapified. So now we need to come back up here and actually do the array sorting. So there we've done all that work to make the array into the format we expect. Now we just need to for int I equals array.length -1, I less than 0, I minus. So work our way back down. This is the this time. This is the operation when we're going through and grabbing the arrays. We start at the end and work our way up. We've done a min array, which you could do a min array, you could do it the other way, maybe. I've always seen it as doing it max, I'm saying array, min heap instead of max heap. I've always seen Max Heap for actually sorting, but I suppose you could do it either way. And to do that, you would just swap the direction of these. And it would be smallest instead of root, and you would work your way the other direction, I think. So I'll keep it this way because this is the way I've actually seen it. So now we'll swap the positions here. So utilities.swap array at 0 and I. So I we're using as the end of the array. So it's the heap size. And as I shrinks, heap size shrinks. That lets you only deal with the values once. This is the operation as I was going through. The heap was getting smaller. That's what this is actually doing, is this step. Notice the array isn't actually changing. It's still staying the same size. It's just where we're keeping track of as the end of the array is changing. So then we'll just have, after you're done, then we have to do that heapify step. And we'll do that. So we say the heap size is that, and the root is the beginning. That, I think, should get us a sorted array. Let's go test that out. So let's see. So quick sort is on. The reason quick sort is on, after we finished the video, I said I would go back and run quick sort with 1,000,000 elements, and I did, and we got about what we expected. It was pretty much, oh, I've got it open already. It's pretty much a 10 times the 100,000, so it was exactly what we expected. In fact, the 10,000 is the one that's a little odd here. But yeah, so we can do heap sort array. And there we go. We should have a heap sort now. Let's see if we get a sorted array. We'll do 10. Pretty quick. And we think we are sorted. So if we do something bigger, let's say we do 100,000. Let's see if it's sorted. Yeah, let's allow duplicates. Now we can allow negative numbers as well. Sorted is true. So there's us a heap sort. So code-wise, it's harder to explain than to actually do. Basically, you're just going through and we need to know how to find the child elements. That one can be tricky to think about, but once you figure out that this one just is always these are its two children. This one, the next two values are its children, and then it just keeps working out like that. And then that's what the heap's actually taking advantage of. Other than that, though, it's just working its way up and down the array. So that's a heap sort. So let's gather some statistics. If we do 10, we got those numbers. So 15.9, which is very slow. Min is 0.2 and 0.46. 100. So if you remember from quick sort, these aren't that fast. And that's what you're trading off here. So for a heap sort, you're trading off speed on the smaller values because it has to do a lot of work to set up the heap and maintain the heap. Oops. That was the same one. 1,000. So you're really trading off your speed for setup. And the setup pays off a little more as you get bigger and bigger numbers. So if we do 1,000,000 here, I think we'll see that this one, if I'm thinking about this correctly, we should see this probably beat merge sort. I don't know that it'll beat quick sort still, though. We may need to go higher or try something that's a little worse for quick sort. Notice on this also their maximum runtimes are pretty high. There's a couple heavy ones there, and then it settles in. 10,000. So relatively speaking, this is filling a lot quicker, but again, I'm still colored by the first ones, how long they actually took. I think I did insertion sort. I think for 1,000,000 elements, it was in the minutes. I did not write it down. 50,000. That's on the fast side. Um, 100,000. I broke my graph here by adding the 1,000,000 case, but not adding any middle ground to it. Finally, 1,000,000. Make sure I actually got 1,000,000 there. And there we go. There's us our data points. If I can finish typing them in. This graph, little interesting at the start. The growth there is hard to see it sloping, but it's sloping a little bit. So to me, it looks steeper, but if you look over here at the scale, it's not really steeper. It's actually narrower. So let's copy these. Here. So comparison-wise, average times are actually faster than quicksort across the board here. Except the very first one. Was it faster than merge sort? I think it was. Interesting. That is actually not exactly what I expected. I was actually expecting quicksort here to stay faster. Grab this category. Yeah, this one's still faster. So here they're much more in line, and quicksort's beating it out a little more frequently. That's more of what I expected to see. Let's run that one with 1,000,000 cases though. Let's try that one. That was this one. Let's run it with 1,000,000 cases. Let's see what happens. A little slower. There you're starting to see the heap start winning out a little bit. You grab those values as well. So there we get 1, 1. I just care about average. 4,383.12. So interestingly, it outperformed it quite a bit there. That looks a little suspicious to me. That looks like 10 times, and it should not have been 10 times. But I guess this one increases by quite a bit too. This looks about what I expected. These look a little slow. I may have something wrong still in my sorts. I may have to go back and look, but this is what you should expect in general. Heap sort generally performs better as you get to larger and larger numbers. So in fact, I bet heap sort's decently fast still on 10,000. I bet it takes us longer again to generate 10 and then, or 10 million than it does to I bet it takes us longer to generate the array here than the run through. Yeah. That's fast to be sorting through 10,000 or 10 million numbers. Oh, got to see 100 million while we're here. 6. Yeah, you can hear my computer spin up as though it did that one. Yeah, that one may be too slow. But that's, there we go. But yeah, that's the heap sort. So while that's running, the graph there looks little, you can see a little bit of a curve there, but it looks pretty steep. It looks sort of linear-ish. It's not really linear because the numbers are a lot bigger and it is going up correctly, but a little hard to see there. Yeah, it sort of has the weird start like merge sort. And quick sorts. So that's the last of the in-log-in algorithms, and it's pretty quick, relatively speaking. I always liked it as well. I actually have never actually implemented it in anything myself, except just examples. But it, like I said, it's the one that if you use the standard sort or the sort from the C# library, that's the sort you're actually getting. It's only about halfway through. So that's basically what we want to cover today. And that brings us to the end of the 6 sorts I was going to cover. So we have bubble sort, selection sort, insertion sort, merge sort, quick sort, and heap sort. There we go. There, it's sped up a little bit. Yeah, this one's going to be, what is that? About 6 or 6/10 of it. So about a second of run, run. So that's still pretty quick. So of these 6 sorts, what we found is, what we found is there's 2 categories of sorts here. Really, we had bubble sort, selection sort, and insertion sort, and insertion sort was hands down the winner here, like not even close. But it was still, these were in a category of their own, and they are in squared algorithms. Then we got the quick sort, merge sort, and heap sort. They were in their own category of in-log-in algorithms. And of those, quick sort's usually going to win it for medium values. Data here, I already deleted it. Data here actually points that heap sort actually beats it for most of the lifetime. But it was very close here in the middle of the pack. Once you start getting up to the million and 10 million, 100,000 cases, sort or heap sort was winning. And like I said, that's sort of what we expected. Insertion sort is the standard library's use for less than 16 values, and I think it was the quickest. I don't think quick sort beat it. Yeah, average case quick sort was slower. The other 2 weren't even close. So it's used there in the beginning. Quick sort's used in the middle, and then heap sort's used for the big values. And I think that is exactly what our values here show. Merge sort's a little more specialized. Like there's times you could need it, but performance-wise, I don't think it beat quick sort or heap sort. In fact, I don't think it beat them on anything. I think heap sort was categorically better on average speed. I think quick sort was too. Maybe. May not have beat quick sort actually. 1,000. Yeah, it was close if it beat it. Oh no, now quick sort won. I'm off a ledge. So that's sort of what we got there though. But so I think the conclusion here we could draw. There's several we could draw, but basically the first conclusion is to use your system sort. They've probably done the analysis and figured out what the best number of positions are anyway. If you're doing your own sorts, if you have only a couple of values, Insertion sort may be your win. It was for very small number of values. It didn't perform badly. And the algorithm was pretty simple. It was the easiest for me to actually understand directly. It would be the one, if I was actually sorting the numbers, I think I would have come up with. Or it may have been selections. One or the other of them was. Most of the time for normal values, it looks like quicksort's what you would want. And the standard library again shows that. Another thing we've found, besides a meta topic we found, is although you can do your own comparisons here, there's actually better ways to do that. And the correct way to do that in .NET is benchmark.net. You could also use a profiler, or Visual Studio has its own profiler. I think you have to have the Enterprise Edition. I don't know that we have access to it here, but it has one. You could use benchmarks.net. There's Rider. JetBrains has their own solution as well. So that would be the correct way to do this. Instead of doing your own timings, you would want to let something that's done it professionally do it. It takes so long to run that it wasn't worth it for our examples here. Yeah. We also seen it was very easy to get messed up because I messed up the I wasn't correctly cloning it originally, so we had to fix that in the second video. So it's very easy to get it wrong as well. So you always want to be testing what you're doing, and that was useful. Yeah, I think this is going to close our sorting numbers here. Let's do one more thing. Let's do this. Let's compare worst case time. So let's do this. So we'll have our array dot sort. Does that return something? No, it sorts it in place. Good. Array dot reverse. That returns something. To array. There we go. I don't know that I like that any better, actually. I think I actually like the to array there in that case. So there, let's try this. So let's see what happens here. If we run this with 1,000,000 cases, that was heap sort and that was 1,000,000 cases. We ran pretty slow this time. So let me write that number down. So let's try it with the quick sort algorithm, however. So this one's we picked this one for a very specific reason. So let's run this one. All right, so there we go. There's quick sort. I'm putting these in the same order, so quick sort's on top, merge sort's in the middle, and heap sort's at the end. So let's see merge sort. All right, 1,000,000. It performs worse. I think that's sort of what we expected. So let's look at those values. So what did I set up here? So what I set up when I sorted it and reversed it, we get basically the worst case for them. So when you do the when you're creating the heap, you get it, everything's all sorted, so everything's wanting to go in a linked list, and instead you have to adjust it and fix it, so it's having to do a lot of operations. For merge or for quick sort, I think that's the worst case. So we start with one and then pick everything and move them all over, and so you pick a pivot and move everything over. You pick the next pivot, move everything over. Yeah, I think that's the worst case for both of them, and it is for merge sort as well, because you have to go through the entire list. They're all exactly opposite of the way you want, so you always end up swapping them each time. And there we can see that the time here on Heap Sort was terribly outpaced. Let's do this as reverse sorted. Here's sorted. Let's take a look at sorted real quick. Let's do it the other way. Let's just remove the reverse call here. Let's see what happens in this case. Not a lot of difference, actually. The merge sort didn't do anything different. That's roughly the same as before. But if we swap the other sorts, we'll do heap sort first, or quick sort first. See what happens here. Still roughly the same. Grab that and write it. And finally, heap sort. Roughly the same. The thing we can notice from them a number of problems is if we remove that line. Now let me collect all this data once more. Sorry for so many collections. I'm wanting to show how much quicker it is on actually random data versus actually sorted data. It just took me. I thought this would be a good example, but it's taking a little longer to gather than I was actually hoping. You're going to notice here, this one performed about the same for all three cases. I don't want to leave us with merge sorts not useful, basically, is what I'm trying to get to. I'm wanting to say it has some use, it's just slower on average than the rest of these, but needed to craft the data, and I didn't do that ahead of time. Count that, make sure don't cheat it out. Yeah, that number seems a little suspicious to me. I'm wondering if I got the quick sort wrong, actually. Let's just compare it with the other quick sort real quickly. Yeah, I think I got the other one wrong. I guess roughly the same, though. Okay. So here's the data we just collected. So this is the this is the last quick sort we did. So here is the reverse sort. Quick and heap were sort of similar. Merge sort was way outline. Same thing here. Sorted was about the same, and all the values were the same. Merge sort was consistent across all of them, though, because it had to do the same operations every single time. So with merge sort, you have to break everything down into the small pieces and then recombine them. So there's not a lot of difference between worst case and average case. In fact, for quicksort, there wasn't a ton of difference either. For heap sort, on the other hand, there was a ton of difference between doing a good average case versus doing the worst case. So that's something to keep in mind as well. That is a lot of values though, but that's over 10 times as quick as quicksort in that case. So that's one thing to keep in mind as well, that sometimes the data you're doing, and I added those negative and duplicates to be able to control and take more data, but we didn't actually use that. But in doing so, we were able to do, we could play around with the numbers a little more, and you might find other interesting tidbits. For example, I believe, I can't remember which one it is. One of these does a lot better with negative numbers than the other two do, but I don't remember which one it is. But you can play around with the numbers a little more and be able to see if you could find something like that, see if I'm right or not. I may not be correct, but I feel like there was one of the sorts that didn't do well with negative numbers. Either way, though, so there's us sorting. So we'll probably slow down on sorting algorithms now. There's many more you can choose from. You can go look online and find all kinds of sorting algorithms. These are the classics. Maybe some of the more interesting ones you could look into on your own. There's one called Radix Sort. It sorts in a different way than anything else, and for numbers like this, it's really quick. These could be very quickly made generic though, and you could just sort any type of data. Radix Sort, you'd have to look at it, but I believe it only works with numbers. So it's a special case. Some other sorts, there's it's either insertion or selection sort that you do it from both ends. There's all kinds of other sorts we could look into, but I feel like this covers the sorting, what I wanted to cover. We got our information. I'll save the information for now, and we may add other sorts in the future, but I think in the next videos we're going to move to other topics. So, in fact, I think the next one or two in particular, we're just going to hit some random topics I don't think we've actually covered. I was looking back through our videos, and I thought I'd covered disposable, but I don't think we did it directly. And I think it deserves a separate time to look at directly. So I think that'll be the next lesson. We'll be looking at disposable. So we'll call it there. So this has been episode 60 of Programming with Shadow. So this has been sorting or sorting examples. So we'll go ahead and call it with that. So thanks for watching, and have a wonderful rest of your day.